So the problem, lost my mouse. There it is. Nope. There it is. There we go. So compute the temperature prediction of the naked planet model for Venus. The formula for the naked model one, it's if you go in 2.4, it's very at the very end. I have most of the formulas there, and it's the fourth root of L1 minus alpha, and then divided by 4 sigma. The glass model, the only difference is this 4 is a 2. Because you're not dividing by as much, because it's holding in more heat. And all the values were given from the problem. L is 200 or 2,600. One minus the Earth was 0.3. This one, the albedo is 0.7. That tells you how much it reflects. So this planet reflects a lot more. And this is from Stephen's law. It's 5.7 times 10 to the negative 8. And it was there should be meter squared. I forget which unit is meter squared. I didn't write it out. And then you would just calculate it. Well, I think it's this one, K meter squared. But anyways, if you calculate it, if you do not have a fourth root, you can take it to the 1/4 power. So if I calculate the top, I get 780 and multiplying the bottom 2.28 times 10 to the negative 7. And I can take it to the 1/4 power. So a fourth root, your roots are the denominator of your exponent. So a fourth root is 1/4. A square root would be x to the 1/2. Depending on how you have to plug this exponent in, if it's not going up here in your calculator, when you put your caret, the 1/4 has to be in parentheses. Otherwise, it'd only take it to the first power and divide by 4. But you just needed to plug in the numbers. Are you getting the 242? Any questions on that?
So at the beginning, when you were plugging in the numbers, when you put 2,600 watts over meters squared,
Yeah,
the, oh, go ahead.
This one here, the 0.7 is meters squared kilowatts to the fourth. And this one is watts. Sorry, I didn't write it all. So this one is meters squared Kelvin to the fourth. And this one's watts. So then the watts would cancel. The meters squared cancels. And here you'd have kilowatts to the fourth. But when you take the fourth root of it, it just becomes, I don't know why I say kilowatts, Kelvin. This is the temperature. I'm sorry. Now this is a lot lower than the actual. It says on here, the real life temperature is 700. Was there any questions though on this? Any other questions? So this is watts per meter squared. If it's not in meters, when they give you it, you need to put it in meters. Because this is meters squared kelvins to the fourth. And this is watts. This is 200, but the actual is 700. I did not think they would be that far apart, but they are, and we've done it correctly. So this is just a model. It's not taking into an account the anything that might be on that atmosphere. So there's something holding in a lot of heat in that atmosphere, and we're just not taking that into account, because this is the naked planet model where it's assuming no trees, nothing, no clouds to hold in the heat. Any questions on that?
So whenever we're comparing the actual value to the one that we calculated, do we just say that like should we know what should be holding in the heat, or I'm just like a little confused about all of that.
Explanations.
Yeah.
Most of the explanation is just seeing that you understand the problem. There, for the most part, isn't a right or wrong answer. But on this one, because this is so low, you could put the naked planet model. Is extremely let me move that over so you can read it. So something like that, maybe you could add I don't want to use the word things, but I guess I'm going to use the word things. There must be a lot of growth. Or, oh, we could put plants. I don't think there is a lot of plants, but. So there has to be something holding in that heat, or maybe their 0.7 is wrong. Because remember, that's how much is being reflected. But if this planet is this hot, maybe it's not reflecting as much as they think. But something that shows that they're different, that it's extremely lower, they're not even close. And so something's wrong, whether it's there's a lot more heat being held in, and so the naked planet model is not a good example, or their 0.7 is wrong. Maybe it should have been smaller. Earth's is 0.3.
So that number means like how, like if it's closer to 1, it means it's reflecting more, and if it's closer to 0, it means it's absorbing more heat.
Exactly.
Okay.
So if that value is 1, the example they give is a disco ball, everything's reflecting off of it. So 0.7, there's quite a bit of reflection, and therefore it should be a colder planet. But it's not, so something is holding it in.
Okay, thank you.
You're welcome. Any other questions? No? Okay. The other days is the chapter we're going to start today, so we won't go over those yet. Oh wow, that's strong. I thought I opened 3. Okay, so today we're going to start or cover 3.1. There it is. So 3.1 is about networking. There we go. So a network consists of 2 sets, a set N of nodes, and the nodes would be the letters right at the intersection. So A, B, C, D. Most of the time you'll see circles there, like a colored in dot, but they're where your intersections are. So that would be the node. So in this problem, there's 4 nodes. Oh, I did have right here. The nodes are the letters. The links are the line that joins them. So if you have 2 nodes that have a link between them, maybe it's next, but they're neighbors. So A is a node, AB is a link to B. AD is a link to D. So when they're talking about a link, they'll put like the 2 values with it, AB, but if it's just A, then it's a node. So what are the nodes above? The nodes would be A, B, C, and D. Any questions on that part? How many links? There's 1, 2, 3, 4, 5, 6. Here they don't have a node, so these are just straight lines that cross each other. Notice here we have the 4 nodes again, and we have 1, 2, 3, 4, 5, 6 links, just like the other one. Any questions on nodes and links? To see if they're the same network, that means from A in this one, we can go straight to B, D, and C. Here we can go straight to B, D, and C. Oops, this one's wrong. Notice that this goes A, D, and so does this one, which makes these two different because we have a link twice. Now, if we took this out and inserted one from here to here, we would make them the same. Because now we have A to D and B to C, where we didn't have that before. Now these two are the same because there's still the 6 links, but they're going to the same nodes. The way it was drawn before, AD and AD, we had 2 paths going the same. So they were not the same networks, and now they are. So these two, even though they look different, would be the same network. Any questions on that? Because whether you go out and around or straight across, it's still AD. So now the 2 networks are the same. Any questions on that?
Can you please explain that one more time?
Mhm. For the networks to be the same, the links have to be the same. So if we look at the links here,
Mhm.
we have AB, AD, AC, and then we have BC, BD, and CD. So in this first one, that's all the links. If we do the links here, we have AB, AC, this one, AD, BA we already have. AB, BA, same thing. BC we don't have yet. Or BD. And then we have CD or DC. So even though the link is drawn differently, it's still going to the exact same place. So this one here is just drawn out here instead of going over this. But it's still the same link. So these are still the same network. Does that
Okay.
help?
Yeah.
Since this network has only 4 nodes, A, B, C, and D, and the links are complete, this kind of explains what I just said. The AC, the BC and AD just pass over each other. There's no node there. Now, if there was a node here, then they would not be the same because this would be missing a node. But since it's not there, they're the same. Networks model aspects of many social, ecological, and human designed systems. 2 nodes in a network are neighbors if they're adjoined by a link. The degree of a node is the number of neighbors that it has. What are the neighbors for node A, and what is the degree? So if we look here, this one's a little easier to look at than that one. If we look at A, how many neighbors does it have?
Two?
How many links does it have? Notice A has 3 lines coming from it. So it has 3 neighbors. So A's neighbors are B, D, and C. So they have 3. What are the neighbors? So those are the neighbors. What is the degree? The degree is the number of neighbors that you have. Since A has 3 neighbors, its degree is 3. You can also look at the number of links that leave it. Like if we look at C, 1, 2, 3 links. So it has 3 neighbors and its degree is 3. These ones are all attached. So every node is attached to all 3 of the other ones. So they all have 3. We'll do another example. Okay, so if we look at this one, who is the neighbors with node 14 and how many degrees is it?
3?
Let's see, 14 is here. Yes, notice there's 3 links leaving it. So there's 3 of them. So its degree is 3. And if we wanted to know what neighbors they were, there's 13, 10, and 9. So their degree, 14's degree is 3, and they have 13, 10, and 9. Any questions on that? Which node has the most neighbors?
Ten.
Okay, let's see, 10. 10 has 4. Does it any have more? Or is there one tied with 10? There's one more that has 4. So the node with the most neighbors is 10 and 6. Notice 6 has 1, 2, 3, 4. So 6 and 10 both have 4 neighbors. Any questions on that? A path is a network. A path in a network is a finite sequence of nodes, each of which, except the first, is a neighbor of the predecessing one or preceding one. What they're saying is when you have one, to have a path, you go from one to the next one to the next one. For instance, if we went from 3 to 9, one path, I could go 3, 6, 13, 12, 9. Each one was connected to or a neighbor of the next one. For instance, 3 cannot go straight to 13, but 3 can go 3, 6, 13, and then 12 and 9. So any path to go from one node to another, you can count those links, and that's the length. The length of the path is well, you add up the links. But you could also add up the nodes minus 1 because you don't include the first one because you're already at that one. So either count the links or count the nodes minus 1. Now let's try. What is a possible path from 1 to 8? So write a possible path going from 1 to 8.
Is it 1, 4, 5, 7, 8?
1, 4, 5. That will work. That is one possible path. There was more than one. So 1, 4, 5, 7, 8.
Yeah.
So that's one path. What's its length? 1, 2, 3, 4.
5.
If you count nodes, you want to go one less than that. I like to count the lengths because it'd be 1, 2, 3, 4. So if I went from 1 to 8, I'd have 1, 2, 3, 4 links. If you count the nodes, you need to subtract 1. Right here. Is there another path? There's quite a few.
1, 2, and 8.
Yeah. 1, 2, 8. What's its length?
2.
So there's a lot. We can even go the long way and go 1, 3, 6, 12, 14, 10, 8. So there's we could even go 14, 9, 4 if we want to go the scenic route. So there's a lot of paths to get from 1 to 8. Any questions on that? A network is connected if there is one path between any pair of nodes. So to be connected, you have to be able to go from any node to all of the rest of them. Not, it doesn't have to be directly, but it has to be able to get there. If there was a number, another one out here, say 15 was out here and nothing was attached to it, then this would not be connected because the other nodes could not get to that one. So maybe even out here. So that these two groups were not connected. Then this would not be connected. But this alone is connected because I can go from any node to another one through a series of paths. Any questions on that? So as long as they're all touching where that you could go from one to another some way. But as soon as you have one that's broken from the rest, then it's not connected. Maybe this is one community and then maybe this has to be fly to get to this one, but they're not connected. The distance between two nodes in a connected is the length of the shortest path. So we had said there was a lot of paths between 1 and 8, and I think that's what the next one asks. Yeah. There were a lot of different ways to get from 1 to 8. The distance between two nodes in a connected network is the length of the shortest path. This is probably the shortest one, 1, 2, 8. I don't see any that are that are also length 2, but that is definitely the shortest path from 1 to 8. So the distance from 1 to 8 is 2. So when there's more than one option to find the distance, you take the shortest one. So we said the graph above was connected, and we said the path from 1 to 8, the distance would be 2 because that's the shortest route. Any questions on that? If a network is not connected, then starting from any given node A, there are some nodes that are reachable from A by a path and others that are not. The set of all nodes that are reachable from A is called the component of the network. Now what that means, keep looking at this. So the component, if we look back here, if we had this, if we're talking about node 1, node 1 can get to all of these. So these are its component. These are not, because 1 cannot get to them. There's no path that connects them. So the component is the ones that you can get to in your network. A very large component is called a giant component of the network. The assertion that nearly all the important networks in our world possess such a giant component is another way of describing the highly connected nature of our world that we mentioned in the introduction. So a giant component, this would be the main component, and this is one that branched out. Over here branched out. And this would be your giant component. I think it tells us a page to go to for another example. Yeah, here it is, figure 5, 132. Mm. I want to slide it, but it won't let me. Oh, well. Page 132, number 5. Sometimes technology is not my friend. 135. Okay, so there's here it is. Wait, it said figure 5, didn't it? Figure 5, oh, 132. Okay, so here's a network, and it's showing you that the darker blue, that would be your giant component. And from all these nodes in here, we cannot get to the ones that are out here. So that giant component is a network of several components colored differently. Blue might be considered the giant component. Any questions on that? I never thought of using the networking in this matter. And I think it was a really interesting topic. It's in the book, The Indian Vulture Crisis. Difluoronic, it's kind of like an over-the-counter ibuprofen or Tylenol. In the 1990s, it became widely used in India to treat pain with their cattle. This treatment led to a steep rise in human deaths with rabies and also from attacks of leopards. And it took a while before they found the connection or the links. The unexpected links here are a striking example of a connected nature of our world. The key link in the chain is provided by the Indian vulture. 133. I didn't want that to go big. So this vulture, they used to have hundreds of millions of vultures. And what happened was the cows are sacred. And so that's why they were giving them medicine for pain. And when they die, their burial system is to let them go back into the earth. They leave them out. And then vultures would eat them. And that's why the vulture population was so large. Unfortunately, some of them are nearing extinction now because the diclofenac attacks, I believe it was their kidneys. And so then the vulture population was dying. Dogs were coming in and eating the cows, becoming sick, attacking people, and having rabies, which gave more people rabies. Because there were so many sick, then the leopards started coming down because then they were able to attack the dogs because they could catch them since they were sick. And so it was just a cycle. They show the networking link on figure 7 right here. Now notice this link has arrows. The arrow goes from the vulture eats the cow, the dog eats the cow. Because these are becoming ill, leopards came in and attacked the humans and the dogs. The dogs gave the humans rabies. Now this one, the dog wasn't actually attacking. It was because of the rabies and a bite. And that's why it's a dotted line. But it shows the links of the Indian vulture crisis. The solid arrows show direct predation. The dash arrows represent the affected dogs on humans via the transmission of rabies. So they weren't actually eating or attacking the human. It was just they had rabies. And so then they passed it on to the human, probably a bite. But the arrows show you which way the predator goes. So vultures, the predator, it eats the cows. Any questions so far? So a lot of different things, if they start looking at what's attacking what, they can find what caused the whole crisis. But now there's only thousands, if that, of vultures, the different vultures. These arrows are called a directed network, a network in which each link is given a direction, such as predation network in figure 7, or varying strengths is called a directed network. The stock flow systems that we were using in chapter 2, when we showed water going into the tub, water going out with those arrows, those were directed network. A node is a network exhibit. A node in a network exhibits triadic closure if every 2 neighbors in that node are also connected to each other. So for every neighbor, 2 of your neighbors, they are also connected. The clustering coefficient of a node is the number of actual links among the node's neighbors, dividing by the number of possible links. Now, one thing you could think about, Snapchat, Facebook. So if I have a Facebook account and I have 20 friends, if those friends are friends, then each of those links makes my clustering coefficient. So if I had 20 friends and say 5 of them were friends with one of my other friends, then that's 5 of them. So that makes your clustering coefficient. We'll have a formula for it in a second. So if we look at page 135. That's not gonna come They have the 2 definitions, but we want to look at this one here. So if we look at figure 9, that's this one here. Looking at G, it has 3 red lines. That means it has 3 neighbors. G is friends with D, E, and F. So D, E, and F. But notice of those friends, D, E, and F, only one of those connect. So of 2 of his friends, they know each other, but nobody knows F. So E and D know each other, but they don't know F. There's only one green link between D and F. Think of G's friend as being friends. there's only one. Thus, the clustering coefficient is 1 out of 3 because there was 3 possibilities. Notice the 3 green lines. Unfortunately, only one of them was friends. So you're looking at all the possibilities, that goes in the bottom. And then on top is the ones that are. Any questions on that? We're going to look at a formula for it. When it gets too large to try and count them, here it wasn't too hard to see that he only had 3 friends, so then ED, EF, and FD would be the links for them to be friends. And it was only one of the 3. But when it gets large, there's formulas you can use. We don't have to count. If D is the number of neighbors a node has, then the number of possible links among those neighbors is this formula, 1/2 D times D minus 1. G had 3 nodes or 3 neighbors. So if we plug it in here, 1/2 3 times 3 minus 1, that would be 6 divided by 2 is 3. So that's the total possible ones. Corresponding to our hand count on the number of possible links of G's neighbors, using the formula saves a lot of time. We'll do an example. So if we look at C here, what's the number of neighbors that C has?
2? Oh, no, 3.
What you want to do is look at C
4.
and yeah, there you go. The number of links that leave it. And so C has 4. They are A, B, D, and E. So A, B, D, and E. The number of possible links. So we could count all of the possibilities, but when there's 4, it's a little harder than when there's 3. So to find them, we can plug the number of neighbors, which is 4, into this formula. So we have 1/2 times 4 times 4 minus. Are we getting 6? So the number of possible friends of his friends is 6. Any questions on that? So we know the possibility of 6, but how many really are there? So if we look at C, we have A and B are friends. So A, B. B, D, that was one of them. E, yeah, E was one, right? Yeah, so this is one, D, E. So we want to find all the links, like A, B is 1, but A doesn't go to D and A doesn't have a direct link to E. Then go to B. B has a direct link to D, but not E. And then DE has one. So I found 3. Is that what everyone found, or is there more? So what you want to do is look at the friends and see all the connections, just a straight one link. And A to B has one link, but A doesn't have a straight link to D or E, so that was only AB. Then I go to the next one. B and D has a straight link, but B doesn't go to straight to E. So that's the BD. And the last one, DE, does have a link. So it's 3 of them. The clustering coefficient is the number of actual links between neighbors, which is 3, divided by the possible, which is 6. 3 divided by 6 is 1/2. Any questions on that? There's not much more, but we'll finish it tomorrow. I think you have enough that you can do the homework problem, but try it and see. And if you have questions, we'll cover it tomorrow. Any questions? Positive?